Hello everyone. In this segment, we are going to see a couple of example of our division algorithm. We are going to see that we can represent a natural number in different base. In generally, actually, in our day-to-day life, we use the number, and we use the number, and we represent the number with a base 10. If the base is 10, that means that in any number, all the digit that we are using, it is going to be all the digit we use, it is going to be from 0 to 9. So in base 10, all the digit we use from 0 to 9. So just represent any number 5 2 6 7, let's say 5 2 6 7 9. You can see all the digit that we are using here, that in base 10, all the digit is going to be from 0 to 9, means less than 10. Okay, so how we represent a number in various base. So in day-to-day life, we use in our natural life, like in our normal life, we use our all the numbers in base 10. So what does that mean? That in that case our b value equals to 10. Now we can actually represent the number in different other bases. Some popular base, it can be b equals to 2, 8 or 16. Okay, and we use base 10, but other base could be 2, 8 or 16. All right, now what does that mean is that for any base belongs to a natural number, then the base b representation of n belongs to natural number, it represent is like that. Okay, and here b is going to be, actually we write it like as a subscript. Okay, so any number we write it like that. For example, say this is our number in base 10, 5 2 6 7 9, we write it like that. Okay, but we do not generally write it like that because this is the most common base we use, or so you can say that this is the default base. So if we do not write the base of which base we are using, that means by default we are using the decimal base or the base 10. Okay, but in all other base, for example, if the base is 2, in that case all the digit we can use to represent a number is going to be only two number, 0 and 1. Means all the number has to be, the digit has to be less than 2. Okay, so all we are going can use, we can use only 0 and 1 in base 2. So it can when then we can, sorry, 1011, then we have to say that this is base 2 and we write it like that. Okay, the base is, we are going to write it like that. Okay, so all the numbers here are in base 2, so that's not like 110 or something. So this number is a number in base 2. So in base 8, we can write it like that. Say in base 8, all the digit we are going to use, that has to be less than 8, means 0 1 2 3 4 5 6 7. Okay, that's 8 number we can use from 0 to 7. So it can look like 5 6 7 0, but if this is in base 8, we have to write it like that. Okay, now the good thing is that all the numbers in any base, we can represent it like that using this formula. Okay, so 0 1 2 3, this means these are the position in the number, the position of the number, the position of the digit in the number, the places. All right, so b is the base and a0 is the number at that place. Okay, say for example, if we have a number 987, okay, and in 10 base we can represent it like that. So 7 is the place 0, 8 is the place 1, 9 is the place 2, right? So we can represent it like that. 9 times 2, so place is 2, so we are going to represent it like that. B times, where b is our 10 to the power 2, plus we have 8, place is 1 and base is 10, so 8 times 10 to the power 1 plus 7 times 10 to the power 0. Okay, so that will give me 900 plus 80 plus 10 to the power 0 is 1, so 7, 9, 87. So any number I can represent, any natural number I can represent in any bases like that. Okay, whatever the base is, I can represent it like that. Okay, the digit and the base to the power the places of the digit. Okay, now if for example this one is a binary number, okay, 101, that's a binary number, means b equals to 2. Okay, so that's my place 0, that's my place 1, that's my place 2. All right, so how I can represent it? So 1 times 2 to the power 2 for this one, plus 0, its place is 1, so 2 to the power 0 times 2 to the power 1 plus 1 times 2 to the power 0. So that will give me 4 plus that 0 and 1, so 5. So and that's in decimal number. Okay, all right, we are going to actually see a couple of examples, so don't worry about that. So let's see, try to find out the binary number to decimal expansion. All right, so remember this formula, and I'm going to just write it like that. So I can represent any number n equals to like that, say so the number is like that, a times n minus 1, b is our base to the power n minus 1 plus a times n minus 2, b to the power n minus 2 plus we're going to continue it like that. So a1 b to the power 1, a0 b to the power 0, and it will be like a2 b to the power 2. Okay, all right, so let's find the decimal expansion of a binary number. So here I'm going to use an example like this. So if the base is 0, then we say the number is a binary number. All right, so in a binary number, all the digit possible we can use only 0 and 1. Only two digit we can use to represent a number, and these numbers are 0 and 1. Okay, and all the numbers that we can use, that has to be the less than base. Okay, so 0 and 1 all are less than 2. So now let's find out the decimal value of this number. Okay, so the places are here 0, 1, 2, 3, 4, 5, 6, 7. Okay, so that will be our 1 times 2 to the power 7. Okay, plus 0 times 2 to the power 6 plus 1 times 2 to the power 5. So in the fourth place we have 1. Okay, and that's 2 to the power 4, 1 0 1 1. Okay, then I have 1 1 0 1, so let's just write that down. 1 1 0 1. Okay, and let's write the base here. So that will be 2 to the power 3, that will be 2 to the power 2, that will be 2 to the power 1, that will be 2 to the power 0. Okay, so this 2 is our base 2. Now we are going to just calculate all of these things, and here there will be some of the items we can just keep. So for some of the number we have 0 times something, that means they are just 0. Okay, for example like this and this, so you can just consider the non-zero number. So that will give me like 128. All right, so 32, 16, this is 32, that is 16, that is 8, that's 4, and that's 1. Okay, so finally it should give me 189. All right, and that's actually in base 10. Okay, you can write it with base 10, or you can just write 189, because the default base we use base 10. Okay, so if we do not include the base in the number, that means this is in decimal number. Okay, now if we have a octal number, how do we represent the decimal expansion? How we can do that? So it's actually the same thing. So in octal number, we write it using the base number like that, and all the digit we can use that has to be less than 8. So that means we can use only all the numbers 0, 1, 2, 3, 4, 5, 6, 7. These 8 digit we can use to represent a number. Okay, so let's see, the number, octal number is 4072. Okay, you can see that all the numbers are less than 8. All right, so here the equation is actually same. This is the good thing. All right, and our base b equals to 8. So we have the places here 0, 1, 2, 3. So that is going to be, the decimal expansion is going to be 4072. So times 8 to the power 3 plus, for this one 8 to the power 2 plus, for this one 8 to the power 1. Okay, plus for this one 8 to the power 0. Okay, so I can skip this one because this is 0, and this is going to be 8 to the power 0 means 1. This will be 2. Okay, so this value, this is going to be I guess 2048. Okay, this will be 0, and this will be 56, and this will be 2. Okay, so finally it should give me 2106. Okay, and that's in base 10, or you can just write it 2106. Okay, now hexadecimal. Hexadecimal means I am going to have like 16 digit to represent a number. Okay, 16 digit to represent a number. So in decimal number we use from 0 to 9, so that's 10 digit to represent a number. But in hexadecimal I have actually like 16 digit to represent a number, and these digits are actually 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10. Then we are going to use the value A, B, C, D, E, and F. All right, and the decimal value for these numbers are A means actually 10, B means 11, C means 12, the decimal equivalent of D is 13, E is 14, and F is 15. Okay, and you can see that all the numbers are less than 16. All right, so an example of hexadecimal number, it could look like 2A, say E, okay, 0, B, and we are going to use the base 16 here. All right, but the good news is that I mean, it may look complicated, but the good news is that it's actually the same formula by which we can make the decimal expansion. Okay, so let's see. 2, we have A, E, 0, and B. All right, now these are our places, so 0, 1, 2, 3, and 4, and our B equals to 16. So what we are going to do, for 2 it will be 16 to the power 4. For A we are not going to use A. All right, so we are going to use the decimal equivalent number. So I'm going to just use okay, so let's do that. So A, the decimal equivalency is 10, so it will be actually 10 times 16 to the power 3. So times 16 to the power 2 times 16 to the power 1 times 16 to the power 0. Now E has the decimal equivalency of 14. Okay, so this is actually 14, and B is the decimal equivalency of 11. Okay, so now we are going to do the calculation. So this is actually just writing 2 times 16 to the power 4, that's not A, 10 times 16 to the power 3, so that's not E. 14 times 16 to the power 2, like that. So 11 times 16 to the power 0. So that should actually give me the value of 175,625. Okay, and in decimal, in base 10. Okay, and or you can just write 175,625. Okay.